Finding the absorbance of a solution based on molarity.
Introduction. Some key terms for this lab are absorbance, transmittance, molarity, and Beer-Lambert's law. Absorbance is a measure of the capacity of a substance to absorb light of a specific wavelength. Transmittance is the ratio of the light energy falling on a body to that transmitted through it. Molarity is a concentration unit, defined to be the number of moles of solute divided by the number of liters of solution. And Beer-Lambert's law is a law that states the relationship between absorbance and concentration of an absorbing species. Spectrophotometer. The spectrophotometer is an apparatus for measuring the intensity of light in a part of the spectrum, especially as transmitted or emitted by particular substances. How it works. A spectrophotometer works by having a lamp provide a source of light. That source of light, in way of a beam, strikes something called the diffraction grating, which works like a prism and separates the light into its component wavelengths. The grating is rotated so that only a specific wavelength of light reaches the exit slit, just like this. It goes from each color and only shines one color at a time. Then the light interacts with the sample. From this point, the detector measures the transmittance and absorbance of the sample. Transmittance refers to the amount of light that passes completely through the sample and strikes the detector, like I said before in the previous slide. And absorbance is a measurement of light that is absorbed by the sample. The detector senses light being transmitted through the sample and converts this information into a digital display. The purpose of this lab was to identify the relationship between the molarity of a copper sulfate pentahydrate solution and its absorbance. And as you can see, this graph here illustrates just that. It illustrates the relationship between the absorbance and the molarity of the copper sulfate pentahydrate solution. And this here is the exact equation that could be used to calculate the molarity. The guiding question for this lab is, what is the quantitative relationship between absorbance and concentration for a colored solution? In this lab, we showed Beer-Lambert's law. Beer-Lambert's law states that absorbance of a material sample is directly proportional to its thickness. It is used as a sort of reference or technique to discover the concentration of certain solutions. The graph that we got as our final result for this lab 2 slides ago, this is exactly that. This is a calibration curve, which is used for reference when you have a certain absorbance of a solution and you want to find the molarity. This is a sample calibration curve of a nickel solution. This calibration curve will aid us in the future when we're using copper sulfate pentahydrate solutions and we need to find out their molarity, so we can just measure the absorption and therefore calculate the molarity.
Materials needed for this lab includes distilled water, a scapula, pipettes, copper 2 sulfate pentahydrate, 5 volumetric flasks, weighing bolts, a test tube, a spectrophotometer, and a scale.
Methods. With the 5 volumetric flasks, fill each up to about halfway with distilled water. For the first solution, weigh about 0.2496 grams of the copper sulfate pentahydrate and add it to one of the half-filled volumetric flasks. Then label it 0.01 molar. After putting in the copper sulfate pentahydrate, fill up the rest of the volumetric flask with distilled water up to the 100 milliliter mark. For the next solution, weigh out 1.248 grams of the copper sulfate pentahydrate and add it to a volumetric flask, then label it 0.050 molar. Then fill up the volumetric flask to the 100 milliliter mark. For the third solution, weigh out 2.496 grams of the copper sulfate pentahydrate and add it to the volumetric flask, then label it 0.100 molar. Then fill up Then fill up the volumetric flask to the 100 milliliter mark. For the fourth solution, weigh out 4.992 grams of the copper sulfate pentahydrate and add it to the volumetric flask, then label it 0.200 molar. Then fill up the volumetric flask up to the 100 milliliter mark. For the fifth and final solution, weigh out 7.488 grams of copper sulfate pentahydrate and add it to the last volumetric flask, then label it 0.300 molar. Then fill up the volumetric flask to the 100 milliliter mark. After all of the solutions have been made, fill a test tube with just distilled water and place it in the spectral photometer to zero it. Once you have zeroed the spectral photometer, dump the water out. Then add a drop or two of the 0.01 molar solution and dilute the water. Then dump out the little solution, add 7 milliliters of the 0.01 molar solution and test it for its absorption. Do the same for the 4 other solutions and record the data. After doing that, repeat the absorptions again to make sure the data is accurate. Repeat the finding and absorption for all 5 of the solutions.
Results. After completing the lab, we created a table using the data we recorded. What we recorded was what the absorbance was for solutions with different molarities, and from that we found that the independent variable, which is the value that does not depend on another, was molarity, and the dependent variable, which is the value that does depend on the other, was the average absorbance. Here we have a picture that shows the different solutions we made after mixing certain amounts of copper 2-sulfate pentahydrate to create a 0.01 molar solution, 0.05 molar solution, 0.1 molar solution, a 0.2 molar solution, and lastly, a 0.3 molar solution. We found the amount of copper 2-sulfate pentahydrate we needed to add to distilled water to create a 100 milliliter solution by using the equation molarity equals moles divided by liters. Here we have a sample calculation showing how we found how many grams of copper 2-sulfate pentahydrate we needed to create the 0.01 molar solution. As you can see, we first calculated how many moles we needed and then changed this value into grams. After typing the data into a table in an Excel spreadsheet, we were able to create this graph showing the relationship between the molarity of a solution and its average absorbance. From this graph, we created a trend line with the equation y equals 2.527 times x plus 0.049. In addition to this, we also found the value of r squared. R squared is a statistical measure of how close the data is to the trend line, and is always between 0 and 100%. In general, the higher the r squared, the better the model fits your data. And for our graph, the r squared value we got was 0.984, or 98.4%, meaning the data we recorded almost perfectly matched the trend line.
Conclusion. The quantitative relationship between absorbance and concentration for a color solution is that they are directly proportional and have a linear relationship. Our data shows that as the concentration of a colored solution increased, the absorbance of the same solution increased also. This experiment proves that Beer's-Lambert law is true because this law states that absorbance is proportional to the concentrations of the attenuating species in the material sample, which is exactly what our lab data shows.
In our error analysis, we will be talking about trendline deviation and y-intercept inaccuracy. Some possible ways that an error could have been made to cause the deviation and inaccuracy is possibly scale calibration. The scale might have been out of place while measuring the copper sulfate pentahydrate, and therefore we could have gotten the wrong measurement and therefore wrong molarity and wrong absorbance. Therefore that would throw off our line. Another error that was possibly made is an error in the actual massing. The scale might have not been set to 0, or we might have not gotten the exact number that was needed. The next one is improper mixing. It is possible that when mixing, the solution was not completely mixed together, therefore it wasn't fully a mixed solution, there were still particles floating around, and that could have also thrown off the numbers of the absorbance. The spectrophotometer might not have been calibrated. The blank sample that we used might not have been a blank, and therefore it would have also thrown off the absorbance of the copper sulfate pentahydrate solution. The final error possibly made is the test tube alignment for the spectrophotometer. It is possible that by mistake the test tube was not placed correctly in the same or correct alignment, and therefore throwing off the absorbance measurements as well.